So actually, before we go into the do now, I'll flip back and then come back to the do now. So for this week, right, this week we're actually reviewing individual units, and then we're going to do practice multiple choice questions. So you guys know the AP test is split into multiple choice and free response. And so today we're actually reviewing units 1 and 2. Tomorrow we're going to look at unit 3. Unit 3 is the largest percentage of the test. It's about 20%, but still that's the largest out of the 9 units. So we'll look at unit 3 tomorrow, unit 4 Wednesday, 5 Thursday, 7 and 8 Friday, and then 6 and 9, which is thermochem and thermodynamics, on Monday. As we review each unit, I'm actually putting together practice multiple choice questions for each unit. So what I've actually been doing is I've been going through a few different practice tests and finding questions that correlate to each unit and putting them into practice like Google Docs. And so the practice that we'll be doing, like, we will get enough practice. I don't think going back and looking at mastering is going to be as useful as actually focusing on some of these multiple choice questions. In terms of homework, each night you'll watch 1 or 2 of the most commonly missed videos that I made last year. So you'll see, like, unit 1, I'm sitting outside because it was in March when I made these. So I put these most commonly missed videos into Edpuzzle. You get points for watching each one of them. So it's just like they were content videos like we did during the year. I put them into Edpuzzle. So since we're reviewing units 1 and 2 today, I'm going to have you watch both of those tonight. Today is the only time you have 2 videos. Every other night is just 1. But within there, I put helpful info. I added some extra multiple choice questions just to help. And that is based on the most commonly missed topics from my classes last year, but they typically don't change. So like Mass Spec is a very commonly missed unit 1 topic. And so I talk about the most commonly missed in each unit. That is the actual homework. That's what you get points for. I have recommended chapters for Crash Course. If you don't read it, I don't know that. All right, the Crash Course is just to help review content. So if you can't find your notes, or you can't find your notes from during the year, the Crash Course book goes into the detail of the content. They're still short chapters, but that goes into kind of the detail of the content. But you can use your notes to help. So as we talk about Lewis structures and shapes, you have your notes that went into more detail on Lewis structures and shapes. If you want to see how our units compare to the AP curriculum, I went through and I made this document. So this is one of the things that you picked up. So you'll see our unit number, which also went with, like, our unit 1, for example, is chapter 6, 7, 8, 9. And so in there, we have all of the different topics that we did, and then how that corresponds to the AP units. AP's first 4 units are kind of all over the place. And so I did it more like we did all the solids at once. AP split solids into their unit 2 and unit 3. As we go through everything, as we go through stuff today, I'll tell you more specifically where you could find the stuff in your notes. And other classes were just writing it in. And then I think I mentioned this last week. I can't remember if I mentioned it to everybody or not. We usually do a 50-question multiple choice final exam somewhere around the day of the AP test. 2 years ago, we did it the day before. But I know there are other AP tests right before and right after ours. So in place of a final, instead of having a big final all at once, we're going to do shorter review multiple choice quizzes as we're reviewing. So you'll just kind of review like 3 units at a time. I'll tell you when they are. They're not like pop quizzes anytime. Like, you'll know when they are. So the first one is Thursday on units 1 through 3. They are all old multiple choice questions. So these quizzes will be curved. Normally our quizzes weren't curved because these are all old AP questions like your tests. And this would be, a final exam would be curved. So these quizzes will also be curved. So you'll be able to see what your score actually was, and then it'll curve using the AP curve that we use. And so again, crash course, those are just recommended. I would recommend that you read them, but again, if you don't read them, I don't know that. And so before we get into the unit review stuff for today, I'll talk about the other stuff that you picked up once we get into the unit reviews. But for the do now, there are 3 questions. I'm going to be putting practice questions, multiple choice, and free response up as the do now from now until, 3 weeks, right? The AP test. So we can practice doing multiple choice. We can practice doing some short free response questions. Since we're focusing pretty much on multiple choice this week, you don't actually need a calculator. And we'll practice doing multiple choice without a calculator more on Wednesday. But you can see in number 1, this was a math-based question, but notice how you didn't actually need to solve. So this says, which of the following expressions gives the number of moles in 5 grams of calcium oxide? So your given information was 5.0 grams of calcium oxide. And it wants to know, how can we calculate moles? So what I recommend doing, if you have a multiple choice question that is math-based, do the work first. Do the work and then see which of the answer choices matches what you wrote out. So I want to go from grams of calcium oxide to moles of calcium oxide. Well, what can I use to convert between grams and moles? Molar mass. When you look at your periodic table and you're doing multiple choice, round. Don't use decimals. So calcium is 40.08, round to 40. Oxygen is 16. So the molar mass of calcium oxide is 56 grams per mole. Now, even if you read it like this, some people look at the answer choices and they're like, and they start like getting in their own head. And they're like, well, maybe it's this one, maybe it's this one. Write out how you would plug it into the calculator. So I would do 5 divided by 56. Pick which one of these answer choices is 5 divided by 56. All right, that's B. Too much. So there are a lot of multiple choice questions that are like this, where you're setting up the expression. You're not actually doing the math. Some of them you are doing the math. But a lot of them you're actually just setting up the expression. So then number 2, a 1 mole sample of which of the following compounds has the greatest mass? So if you have 1 mole of each of these, well, you can look at the mass of 1 mole. Look at the molar mass of each of these. Right? Look at molar mass. Now you don't have to actually add all of these up. Just look at these and see, based on the formula, which would have the greatest molar mass. So which one of these would actually have the greatest molar mass? Right, D. You have 2 N's and 5 O's.
Is that like the difficulty of the AP test?
These are practice questions.
Seriously?
These are all practice for Unit 1. Now, topic 1 of Unit 1 is like converting between grams and moles.
Really hard.
But then we get to like number 3, and then people are like, oh no, electron configurations.
That's the easiest part.
I love
it. It's just like so much fun.
Right. So here's the thing with this, and I'm going to talk about this when we get into the unit reviews. Orbital diagrams are not technically written out in the curriculum. Nowhere in the curriculum will it say orbital diagrams. However, we've seen a lot of questions that include orbital diagrams or that will help answer questions like this. So when you have an electron configuration, remember you can represent an electron configuration using orbital diagrams. Always look at your outermost electrons. That's where you're going to find if there are any unpaired electrons. Now we can see this, it's 3p6, which means it's filled. If it's filled, Do you have any unpaired electrons? No. So our answer is actually A. But what we can do is we can actually look at 3p6. Well, remember the 3p sublevel has 3 orbitals. And if there are 6 electrons, we have 1, 2, 3, 4, 5, 6. Every electron has a pair. So in this, there are no unpaired electrons. If this were 3p5, so instead of 3p6, we have 3p5. 1, 2, 3, 4, 5. Well, now we have 1 unpaired electron. So orbital diagrams can help you visualize electron configurations. And we'll look more at electron configurations when we're going through the reviews. Any questions on any of these multiple choice? All right, if not, what we're going to do today, and really what we're going to do the rest of this week, is we'll start class with unit reviews. So I actually just took a screenshot from Google Classroom. I added these unit reviews last night. And so under the classwork tab in Classroom, there's a topic that says AP exam review. So I actually split the Edpuzzle videos and the reviews separate just to make it easy to find. So under AP exam review, here's where we have a lot of the things that we're going to be using often. So the unit guides, that's what I actually had you pick up for Unit 1 and 2. So the packets that look like this are the unit guides. This is the AP curriculum. This is what College Board says you need to know. Right? The essential knowledge is what you need to know, and the learning objectives is how they're going to test the different questions. I put all of the unit guides on Classroom. I will give you copies of the unit guides in class. But if you're ever at home, you can find them on Classroom. That's where the crash course book is, the review playlist, and then the unit reviews. So these unit reviews are Google slide decks that I go through and I add just important information on. What the other classes have done is they've opened the unit reviews. So they've had the slides open on their Chromebooks. And then what first period actually did, and then third period did the same thing, because the unit reviews go in order of the topics. They actually just added any extra notes to the bottom of each topic page from the slides. Now, I would not say that you need to write every single thing on the slide because a lot of it is in the unit reviews or in the unit guides. So if you want to follow along within this material on Classroom, there are 2 drive folders. One is called Review Slides with Practice. So that is what we're doing in class, but then I've added extra multiple choice questions, extra free response to it. So that's almost more of a, if you want to do it on your own time. But then the second Google Drive folder is in-class reviews. Obviously, that's what you want because we are in class doing the review. So if you want to follow along, you can go into Google Classroom. Under AP Exam Review, click on the unit reviews, and it'll open the slides. So this is what the slides look like. And as I go through more, I will obviously put the rest of them up. So like right now, I think you can see units 1, 2, and 3, but I'm not done with unit 3 yet. And I'm constantly making changes. So there were some things in first period that they were asking questions, so then I added it into the slides for third period, and then third period asked questions, so I added it into the slides for you guys. So unit 1 is atomic structure and properties. So this is actually, it's a few different things. It was some stuff from the summer work. It is some math. And then we get into like electron configurations, PES, and periodic trends. So just kind of the general overview. Here are all of the topics in Unit 1. This is actually on the front page of the Unit 1 guide. It says Unit at a Glance. You can see all of the topics. All right, so you can see all of the topics on that front page. And Unit 1 and Unit 2, right, these unit guides are over on the side. So if you have to grab those, you can. And so we're just going to go through each topic. I have them labeled at the top so you know which topic we're looking at. I'm not reading everything directly from the unit guide. I'm like adding different stuff to it. So for 1.1, this is doing calculations. So can you do calculations between grams and moles, between atoms and moles, or molecules and moles, or from molecules to grams? And so this is just all of the different mole calculations. Remember, on the equation sheet, you have Avogadro's number on the equation sheet. So you don't actually need to memorize Avogadro's number. You have it right under atomic structure as one of the constants. Molar volume we'll actually talk about more when we do gases tomorrow. So gases is part of Unit 3. We'll look at that tomorrow. So topic 1.1 is just comparing number of particles. Being able to do calculations, comparing based on moles, like we did in the do now. Topic 1.2. So this mass spectrometry was actually part of the summer work, so quite a long time ago. Mass spec is evidence for isotopes. So topic 1.2, looking at mass spectrometry, this is evidence that elements have isotopes. Remember that isotopes are atoms of the same element. So if they're the same element, they have the same atomic number. Remember, atomic number is number of protons. But they have different masses. So they're atoms of the same element with different masses. And the reason that they have different masses is because different number of neutrons. So carbon-12 and carbon-13, those are isotopes. They're both carbon, but one has a mass number of 12, one has a mass number of 13. A mass spectrum, that's a graph. A mass spectrum helps you identify what the element is, how many isotopes the element has, and a rough idea for the average atomic mass. So this shows a mass spectrum of zirconium, ZR. You know that it's a mass spectrum when you see abundance on the y-axis. Your x-axis might be mass or mass to charge, but our y-axis is always abundance. So notice how here we see 1, 2, 3, 4, 5 peaks. That means we have 5 isotopes. So zirconium has 5 different isotopes, and we can see that zirconium-90 makes up a little bit more than 50% of all of the isotopes that exist. Which means if it asks us a question about what is the average atomic mass, we know that it's probably going to be closer to 90 than 96. Because 96, the percent abundance is maybe 2%. Where the mass of 90 makes up 50%. And so this shows us how many isotopes we have. Based on the mass, we can figure out what the element is, and we could figure out roughly what the average atomic mass is. Now, we saw a calculation on average atomic mass on the 2017 test, I think. And you were actually given a mass spectrum and you were asked to calculate the average atomic mass. It was part of a free response question. Average atomic mass is not on the equation sheet. Calculating average atomic mass. Calculating average atomic mass is a weighted average. So it's like if you want to calculate your GPA, or you want to calculate your grade if you have weighted grades. Well, it's a weighted average, which means if I want to calculate the average atomic mass of each one, I want to calculate the average atomic mass of zirconium with each one of these peaks. So that means that, I'm just going to round all of these numbers. I have 50% with a mass of 90. I'm going to use it as a decimal. Because notice how it's abundance divided by 100. I'm going to use it as a decimal. So 0.5 times 90 plus 0.1 times 91, because it's about 10%, plus, we'll say 18%, 0.18 times 92, same thing for 94, plus, I'll say maybe 2%, 0.02 times 96. Now, if you had to calculate average atomic mass, they would actually give you the exact abundances, because all of these numbers should add up to equal 1, and I don't think mine added up to equal 1. When you take this weighted average, if I multiplied all of these and added these together, it would give me some number between 90 and 96. More than likely, it's going to be closer to 90, probably between 90 and 94, because that's where most of the abundance is. That lets us calculate the average atomic mass. Now, the actual average atomic mass of zirconium is 91.22. The mass on the periodic table is the average atomic mass, and that is calculated by doing what we did here with mass spec data. So average atomic mass is taking your relative abundance times the mass of that isotope. So mass spec data gives us information about isotopes, atoms of the same element with different masses. So then topic 1.3, we start to look at the differences between pure substances and mixtures. Topic 1.3 is, to me, it's a little weird. Because basically topic 1.3 says everything is made up of atoms. The ratio in any pure substance is always the same. So water is always 2 H's and 1 O. Hydrogen peroxide is always 2 H's and 2 O's. No matter how much water you have in a sample. I could have this cup that's completely full, it could be half full. This is always H2O. It always has a molar mass of 18.016. It always has 2 H atoms for every 1 O atom. That's a lot of what 1.3 says. The rest of 1.3 talks about empirical formulas. Now, at the bottom of 1.3, what I would suggest, because the last part, kind of the essential knowledge, talks about empirical formulas. Percent by mass is another way that we can look at composition. So this slide really has two different things, percent by mass and empirical formula. Percent by mass. You want to calculate the percent by mass of something. That's part over whole times 100. So if you want to know what percent of carbon dioxide is carbon, well, you take the mass of carbon that's in CO2 and you divide by the total mass of CO2. Multiply by 100 because it's a percent. So percent by mass is one way that we can determine the composition of a substance. But then we could use percent by mass to find the empirical formula. The empirical formula is the simplest whole number ratio of atoms in a substance. So hydrogen peroxide is H2O2. That is not the simplest ratio of atoms, because I can divide both of these by 2. So if I wanted the empirical formula, it would be 1H and 1O. This is the molecular formula. So if you need to solve for empirical formula, we see this a lot in multiple choice. They make you do this without a calculator, but they give you numbers that you can divide easily. When you have empirical formulas, or you want to solve for an empirical formula, here are your steps. Percent to grams. So if they tell you you have 50%, 25%, and 25%, drop your percent and just put a G for grams. So percent to grams, grams to moles, divide by the smallest, multiply till whole. So you take your percent, turn it to grams, take your grams and convert to moles. You need the molar mass. Remember, these are for single atoms. It's an H atom, an O atom, an N atom. They're not diatomic, it's just single atoms. You divide by the smallest once you get your number of moles, because an empirical formula is the ratio of moles of every substance. If you do not get whole numbers, or something close to a whole number, you multiply until you get whole numbers. So if you get 1.25, you multiply everything by 4. You get 1.5, you multiply everything by 2. This is how you find an empirical formula. The molecular formula is then the actual formula of a substance. So notice how H2O2, that's 2 times the empirical formula. So the molecular formula is a multiple of the empirical. If you know the empirical formula and you know the mass of your molecular formula, you can figure out what the actual molecular formula is. Because H2O2, that molar mass is twice as much as the empirical formula. It's always some multiple. So empirical formula, those are your steps. Percent to grams, grams to moles, divide by the smallest, multiply till whole. But that's one. That and percent by mass are ways that we can look at what is the composition of a pure substance. So then 1.4 is looking at the purity of a substance. So topic 1.4 is looking at the purity of a substance, and a lot of times this kind of ties into 1.3 because we look at how will certain impurities affect the percent by mass. So we have impurities a lot of times when we're in lab. We're in lab, there's some impurity that changes the percent by mass. Let's say that we have water in a substance. You can heat something up to get rid of the water. So we have what are called hydrates. Hydrates are substances that have water attached. We've seen this in a free response question where it says, why do you heat something multiple times? Why do you put something through 3 or 4 different heatings? What's the point? Well, the point is to make sure that any water that was there is completely gone. When we look at free response questions next week, we'll look at some of these questions where it says, what's the point of making sure that the mass stays the same? It's to make sure that we get rid of any water. Then we don't have to worry about there being any impurities. Right? Our substance should just be the pure substance. Now, we actually did this lab at the beginning of the year. We did gravimetric analysis. This actually ties into 1.4. When we are looking at analyzing a substance, we did gravimetric analysis where we took calcium chloride, we put it through a few steps, we created calcium carbonate, which is chalk, we dried it out, and we found the mass. So gravimetric analysis allows us to look at the percent composition of something. We could find the empirical formula of something, or we can figure out how much of a solid we have, and then we can go backwards and figure out what we started with. So with our gravimetric analysis lab, we formed a precipitate. So this is actually what we did. Instead of Pb2+, we had Ca2+. So we had calcium chloride. That was a solid. And the first thing that we did is we added water. We dissolved it. Calcium chloride is soluble. So when we put calcium chloride into water, it broke apart into its ions. So we saw Ca2+, we saw Cl- floating around in solution. Then what we did is we added sodium carbonate. So we added sodium carbonate into that solution. And what happened is the carbonate anions and the calcium cations reacted to form a precipitate. So then in the solution, we still had Na plus and Cl minus floating around because those are spectator ions. But we had this solid down at the bottom. Once we let the solid settle on the bottom, we were able to filter. When we filtered this, right, we had our filter paper, we added everything down. Here was our extra solution of NaCl. We didn't need that, it just went down the drain. But then we had this solid in the filter paper. That solid, we had to dry out 3 or 4 times. We had to put it in the oven in the back, let it dry out to get rid of any water. Now, when we did this lab, we were able to take the mass of this solid and we were able to stoich backwards. This was calcium carbonate. We looked at the balanced equation. We said, well, based on calcium carbonate, how much calcium chloride did we need? And then based on how much we started, how much we needed, we were able to actually figure out concentration that we started with. Now, along with these lab-based questions, College Board loves to ask these error analysis questions. What would happen if? And this is why in the labs that we did, we thought about what would happen if. What are different sources of error, not just my lab partner dumped something on the table. But we looked at different things, and these are questions that we've seen so far. What would happen if the solid was contaminated? You guys actually looked at this question on the very first day of class when we did that penny lab. Right, we did the penny lab on the first and second day of class where we filed in the side of a penny, we reacted it with HCl, and the goal was to actually just get the copper shell. Some people actually had contamination in the copper shell. They still had some zinc left over. Well, if we have contamination in the solid, the mass of what we're trying to measure is going to be too big. All right, we have zinc in with the copper. Well, the mass is going to be bigger than what we expect. In a case of precipitation, right, that's forming a solid. If we have incomplete precipitation, that means that not all the solid formed. Well, if not all of the solid formed, our mass is going to be too small. So you have to think about, if you were doing the lab, what would happen if it happened to you? Right, you took it over to a scale. Would you expect your mass to be too large or too small? This is a very common question. We've seen this in multiple choice and free response. What happens if there's water added? Well, in the case of filtering like this, and this also happened to some people with the penny, it was still wet. Well, if you still have water in a solid or you still have water in the penny, then you're finding the mass of not only the solid but also of water. So your mass would be too large. So topic 1.4 is all about analyzing a substance and what would happen if you had this source of error. We'll look at more free response questions with that one. So then 1.5 through 1.8 really focuses on electrons, electron configurations, periodic trends. So 1.5 focuses on electron configurations. With electron configurations, remember you start with hydrogen and you read across like a book. So hydrogen starts with 1s, you work across 1s1, 1s2, you move down 2s1, then 2, then 2p, and so on. So electrons, we say that they are in energy shells or energy levels. That's your value of n. And then, more specifically, they're in subshells or sublevels. Now, you're going to notice in 1.5, it specifically says you do not have to assign quantum numbers. So remember, we did n, l, m sub l, m sub s. That is not tested. What you need to know is the energy level. You still should reference things as n equals 2 or n equals 3. That makes things easier for you to reference on the periodic table. But in terms of assigning quantum numbers, you don't have to do that on the AP test. Some terminology. core electrons versus valence electrons. Remember, valence electrons are your outermost electrons. So your highest value of N. For example, neon. Neon has 8 valence electrons. Everything in N equals 2. That's your outermost energy level. It's not just the sublevel, it's the energy level. So it has 8 valence electrons and 2 core electrons. Whatever is not valence is core.
It was like the 4s2 3d10. 4s2.
Yes, if you have a transition metal, you had, 4s2 3d10, it's your highest value of N that are your valence electrons. So those are the first ones to go. Yep. And then with configurations, remember we go from lowest energy up, which is why we start with 1s, and then we work our way up. Please read the question carefully. If a question says, write the complete electron configuration, complete means you have to start with 1s and you have to work up. So if it said, write the complete configuration for Na, you start with 1s, you work all the way up to 3s. If it just said, write the configuration, then you could do complete or shorthand. But just make sure that you're reading the question carefully. With electron configurations, you have orbital diagrams as well. So notice how the orbital diagrams are just a way to visualize the electron configuration. S has 1 orbital, P has 3, D has 5. You probably won't see the F block, but the F has 7. Electron configurations were chapter 6 for us. So I split unit 1, like our unit 1 was 4 chapters. They all had different notes packets. Electron configurations and orbital diagrams were chapter 6. So if you want to go back and look at electron configurations, that was chapter 6. When we look at configurations, we can also look at PES. So topic 1.6 was PES. This was also part of chapter 6. Remember, PES, photoelectron spectroscopy, was a way for us to graphically see an electron configuration. On the x-axis, we had energy. The higher the energy, the closer those electrons are to the nucleus, because the harder they are to remove. In topic 1.5 of the unit guide, it talks about Coulomb's law. We'll talk more about Coulomb's law when we look at periodic trends. But remember, the closer the electrons are to the nucleus, the stronger the attraction, so the harder it is to remove. Now we also will see questions on multiple choice that looks at elements with more protons, right? What would that look like? Well, if this is lithium, I'm going to show beryllium in purple. Lithium has 3 protons in the nucleus. Beryllium has 4. So it has 1 more proton in its nucleus. We're going to look at periodic trends. With periodic trends, this is topic 1.7. But before we actually get into the trends themselves, this is more of a please don't miss points on the free response type of slide. You have got to be able to explain periodic trends. And when I say explain, I mean explain. Saying it increases as you go up and to the right is stating the trend. That's not explaining the trend. Explaining the trend is saying as you move across a row, there are more protons in the nucleus, which creates a stronger attraction between the valence electrons and the protons in the nucleus. That's an explanation. So make sure when you are explaining periodic trends, you use Coulomb's law. Coulomb's law looks at charge and distance. You will not be asked to calculate anything with Coulomb's law. All right, you don't even need to know the formula for Coulomb's law. What you need to know is how charge and distance affect the force of attraction. So when you're talking about size or ionization energy or electron affinity, relate every single periodic trend back to Coulomb's law. This is probably the most important thing on this slide. Coulomb's law focuses on charge and distance. you should look at distance between the protons in the nucleus and the valence electrons first. So your first focus is what is the distance between the nucleus and the valence electrons? If you're looking at two elements like sodium and magnesium, well, if you look on the periodic table, sodium and magnesium both have valence electrons in n equals 3. If the valence electrons are approximately the same distance, they're in the same value of n, state that, write that down. So sodium and magnesium both have their valence electrons in n equals 3. If distance is about the same, then go to charge. In the case of periodic trends, when we talk about charge, we're talking about the protons in the nucleus and how they're attracting the valence electrons. Magnesium has an additional proton in the nucleus. It has a higher atomic number, which means magnesium will have a stronger attraction to the valence electrons. Magnesium's nucleus will have a stronger attraction to the valence electrons. If it has a stronger attraction, that's going to pull them in a little bit, which means it's going to make it smaller. That means it's going to be harder to remove one of those valence electrons, but it's a little bit easier for an electron to stick, right? If it's a stronger force of attraction, it's easy to attract another electron. But always look at distance first, then look at charge. So if we actually look at the trends themselves, some people, when we did trends, they wrote the trends on their periodic table. Remember, size decreases. So I just put the same arrows. Size gets smaller as you move across. Size gets bigger as you go down. Size is opposite of ionization energy and electronegativity. When you explain these trends, notice this is the exact same thing that I had on the slide before. Talk about the attraction between the protons and the valence electrons. The closer a valence electron is to the nucleus, the more strongly it's attracted. And so that's distance. The more protons in the nucleus, that's effective nuclear charge. The more protons in the nucleus, the more strongly it's attracted. Sometimes we see some exceptions with ionization energy. For example, O, oxygen, actually has a little bit smaller ionization energy than nitrogen, and that's because of electron repulsion. So with oxygen, you're adding a fourth electron to the 2p, which means you have to pair up electrons in one of the orbitals, and that's going to create some repulsion, and so electrons will repel as well. But typically, we just focus on Coulomb's law. How is the attraction between the protons in the nucleus and the valence electrons? So we're going to focus on ionization energy because it seems like ionization energy is typically the most tested periodic trend. Ionization energy is the energy required to remove a valence electron. Ionization energy increases as you go across a row, but decreases down a group. Here are the reasonings. These are our explanations. It is not, well, because that's what the trend says. You have to talk about attraction. It increases as you go across a row because the number of protons increase in the same energy level. The same energy level means about the same distance to the nucleus. It decreases as you go down a group because the electrons are farther from the nucleus. As you go down a group, so from lithium down to francium, you go from n equals 2 to n equals 3 to n equals 4 to n equals 5. And the electrons get farther and farther from the nucleus. That's that $20 bill example. I put a $20 bill in the back of the room, right? That represents like n equals 7. It's a lot easier for you to go and take that $20 bill away because it's farther. That's ionization energy. The easier it is to take an electron away, the lower the ionization energy. Now, sometimes with multiple choice questions, we have to be able to identify an element based on ionization energy. So if we see something like with boron here, let's say that they give us this data. And they say you have an ionization energy, first ionization energy is 800, then 2400, 3700, 25,000, and 33,000. And it says, what's the identity of the element? All right, maybe they say it's a group or an element in period 2. Period is a row. Look for the jump. Look for the largest jump because that tells you how many valence electrons there are. The biggest jump here is between the 3rd and the 4th electron. Here's the biggest jump. It's over 20,000 kilojoules, which means it's relatively easy to take away the first 3 electrons. It's relatively easy to take those away. Then we try to take that 4th one away, and it's a lot harder, which means that this element had 3 valence electrons. Because if we look at the Bohr model, there's the nucleus, n equals 1, n equals 2. Right? Well, if we were in n equals 2 and there are 3 valence electrons, this data tells us that removing 1, 2, 3. Removing these 3 electrons was pretty easy. Trying to remove the 4th one gets a lot more difficult because now we're trying to remove an electron that is closer to the nucleus. Well, if you're removing an electron that's closer to the nucleus, it's going to be a lot harder because now the protons in the nucleus are attracting those electrons more strongly. So if we notice a jump between 3 and 4, that means that we had 3 valence electrons. Remember, valence electrons are based on the location of the periodic table. Group 1, so lithium, sodium, potassium, has 1 valence electron. Group 2, beryllium, magnesium, calcium, they have 2 valence electrons. We skip the middle. Boron's family has 3, carbon's family has 4, and then we go all the way up to the noble gases, which have 8. So 1, 2, skip a few, and then 3, 4, 5, 6, 7, 8. So an atom has between 1 and 8 valence electrons. This one had 3. If we were looking for an element in the second period, the second row, with 3 valence electrons, if you look at your periodic table, that's boron. These are very common types of multiple choice questions, identifying based on ionization energy data. And you'll see some in the practice multiple choice questions today. And then finally, 1.8. So 1.8 talks about chemical reactivity. Reactivity tends to increase as you go down a group for metals and up a group for nonmetals. So here's why. The easier it is to remove an electron from a metal, the more reactive it is. When metals lose electrons easily, they become cations. That means they become very reactive. Francium, Fr, is the most reactive metal because it has such a low ionization energy. And then for nonmetals, the higher the electron affinity, that's the likelihood of a nonmetal gaining an electron. The higher the electron affinity, the easier it is to add an electron and the more reactive the nonmetal. Fluorine is the most reactive nonmetal. So francium is the most reactive metal. Fluorine is the most reactive nonmetal. When we look at the periodic table, elements in the same group tend to form similar compounds. So if we're looking at how magnesium reacts with halogens, every halogen forms a charge of -1. So whether it's Cl, Br, F, there'll always be 2 halogens for every 1 magnesium because magnesium forms a +2 charge. So that kind of ties into the last part. Charges are based on the number of valence electrons and the location on the periodic table. You have to be able to figure out what charge does something form. Remember when we talked about oxidation numbers? I said that group 1 and group 2 forms the same charge as it would in a compound. Li is always +1, Mg is always +2. Well, if we're looking at forming a compound, we typically see these charges. Remember, carbon's family can be +4 or -4, depending on if it's a metal or a non-metal. Then we go -3, -2, -1, and the noble gases are 0 because they do not react. So this is looking at chemical reactivity. So here we look at the reactivity of metals and nonmetals, how periodicity works with forming compounds, and then charges are based on valence electrons.
What did you say was like the most reactive?
The most reactive non-metal is fluorine.
And then
The most reactive metal is francium, Fr. So they're actually in opposite spots on the periodic table.
I was just showing.
Oh yeah. Yep, so francium is the most reactive metal, fluorine is the most reactive non-metal, opposite corners of the periodic table. All right, so that was Unit 1. Unit 1 is definitely a little bit longer than Unit 2 because we look at periodic trends in there. If we look at Unit 2, so we'll go through Unit 2 quickly. Unit 2 covers molecular and ionic compounds and structures. So now we'll switch from the Unit 1 guide, and you can see how within these guides there's this essential knowledge. That's what College Board says you need to know, but sometimes it could be a little bit more, right? Like configurations, we also need orbital diagrams. For Unit 2, here's where we're looking at bonding. So we're looking at the types of bonds, we're looking at ionic bonds, metallic bonds, and then creating Lewis structures and shapes. Yes, you still need to know your shapes. So for 2.1, topic 2.1 looks at the types of chemical bonds. So 2.1 is actually 2 pages within the unit guide. This looks at electronegativity and polarity. So the electronegativity is the tendency of an atom within a bond to attract a shared pair of electrons toward itself. So electronegativity is about atoms within a bond. It's a tug of war. Fluorine is the most electronegative atom. So when fluorine is in any compound, right, but it's bonded with something else, it's going to pull the electrons toward it more strongly than the other atom, unless it's fluorine itself. Electronegativity increases from left to right, decreases down a group, right? Fluorine is the most electronegative atom. Electronegativity helps us to determine polarity of bonds. So polarity is the degree that electrons are shared within a molecule. If we have something that is polar, so we're looking at a polar bond, 2 atoms are sharing the electrons because it's covalent, but they're sharing them unequally. So that means that you're looking at atoms of different electronegativity. The atom with the higher electronegativity will develop a partial negative charge. Typically, if you have fluorine in there, fluorine is always going to be the more negative one. A non-polar bond is when 2 atoms share electrons equally or fairly equally. That's when you have atoms of similar electronegativity. Remember that CH bonds are always nonpolar. That's why any substance that is only C's and H's is a nonpolar molecule. In terms of polarity, look at the distance on the periodic table. So look at the distance between the 2 atoms on the periodic table. The farther apart they are on the periodic table, the larger their difference in electronegativity. So B and F will actually be a more polar bond than O and F. The farther apart they are on the periodic table, the more polar the bond will be. You do not have to memorize the electronegativity differences. You just need to know that the farther apart they are on the periodic table, the more polar the bond. Now remember, as we look at nonpolar covalent and polar covalent, we still have ionic bonds. Ionic bonds are always between a metal and a nonmetal. You can tell that something is ionic if it's between a metal and a non-metal, or a polyatomic ion. But polar and non-polar, those are covalent bonds. You have non-metals sharing electrons. So electronegativity and polarity help us to look at the types of bonds that exist. Now, the last type of bond, this is still part of 2.1, the last type of bond is a metallic bond. Now, a metallic bond has what's called a sea of electrons. So if you have, here's an example of a metal, you have metal atoms, and then you have these electrons. The electrons are not just fixed in one place. The electrons are able to move all around. That is called delocalized. So delocalized means that the electrons can move around. Metallic bonds have special properties because of the sea of electrons. So it's malleable, meaning it can take different shapes. It's ductile. You can pull metals into thin wires. That's how we can make copper wires. It's a good conductor of electricity because you have these electrons flowing and moving around. So metallic bonds are unique because of the sea of electrons. That's a unique property specifically to metallic bonds. So topic 2.2 talks about intramolecular force and potential energy. Intra means within a molecule. A covalent bond is an intramolecular force. If you want to make yourself a note next to 2.2, we looked at graphs like this in chapter 8. So we looked at this graph, actually on the next slide is the exact graph that is in chapter 8, but this was in chapter 8. A potential energy graph like this allows us to look at the energy and distance between atoms. And so the lowest part of this graph tells us two things. It tells us the bond length, so 74 picometers was the bond length, and it tells us the bond energy. So how much energy would it take to break the bond? Now, some other things with these potential energy graphs. These graphs will be different based on the type of bond that exists. A single bond, so a single bond, which would have a bond order of 1 because it's just one bond, is the longest type of bond. You only have 2 electrons being shared, and so a single bond is the longest bond. Double bond is right in the middle. A triple bond. A triple bond is the shortest bond. Because you have 6 electrons in between 2 atoms, it's the shortest bond and also the strongest. It's the hardest to break. So a triple bond would actually, we would see it down further and actually closer to the y-axis because its distance is shorter. So a triple bond is the shortest bond and also the strongest because you're sharing 6 electrons. Now, if we take a look at this, which was actually from our chapter 8 notes, this shows the same graph kind of on a bigger scale. And it shows what happens as we move atoms closer and farther apart. When you have a potential energy, so the y-axis is potential energy. When you have a positive potential energy up here, you have a very unstable arrangement of atoms. Right? You have an unstable arrangement. When you have a negative potential energy, it's more stable. Now, at this lowest point, this is important. This is an important point on the graph because this is where attractive and repulsive forces are balanced out. So the bond exists when potential energy is the lowest because the balance between attractive forces and repulsive forces causes that to be a stable arrangement. And then internuclear distance is a word that you might see. That is the distance between the 2 nuclei. It's the bond length. So if you see internuclear distance, just know that that's also looking at bond length. Again, that is in chapter 8. So if you want to go back and look at topic 2.2, look at chapter 8 notes. Then we move on to 2.3. So 2.3, we were looking at covalent bonds. Now we're going to look at ionic bonds, ionic solids. With ionic solids, the biggest thing with this topic is knowing that you have cations and anions arranged. Positive and negative will attract. Now I want you to add this to 2.3. Right, write it down somewhere. Cations are smaller than anions. Please remember, cations are smaller than anions. There was a question a couple years ago where all you had to do was identify Li plus and Cl minus in a diagram like this. And a lot of people switch them. Cations are always smaller than anions. And you're always going to see this arrangement of plus, minus, plus, minus, plus, because you don't have any repulsive forces there. They're all attractive forces. When you're looking at the strength of an ionic bond, you can look at Coulomb's law again. Anytime you're looking at strength of attraction, any kind of strength of attraction, you can think about Coulomb's law. Ionic bonds, a lot of times we're looking at the charge. If you're looking at Na plus and Cl minus, that attractive force, versus Mg2 plus and S2 minus. Well, now you have higher charges. The higher the charges, the stronger the attraction. And so if you're looking at the strength of an ionic bond, you can look at Coulomb's law. The higher the charges, the stronger the attractive force between the cations and the anions. But with structure of ionic solids, please just remember that cations are smaller than anions, and plus and minus attract. So going on with metallic solids. So we looked at ionic solids, and now alloys are metallic solids. Topic 2.4, this is directly out of the unit guide. Right? This information is directly out of the unit guide, and I'll show you a particle diagram that you can draw in as well. So metallic bonding, remember we look at the sea of electrons. Two specific types of metallic solids are interstitial alloys and substitutional alloys. I'm just going to put the particle diagram questions on here while I talk about alloys. So interstitial alloys, right here. Interstitial alloys are when you have two atoms of different sizes. You have two atoms of different sizes. One of them is smaller than the other. The smaller atom fills in some of the holes that the larger atoms will create. So here we have a metallic solid. More than likely, these small atoms are nonmetals. And those nonmetals will fit into the holes of the metallic solid. That creates an interstitial alloy. The other type of alloy that you have is a substitutional alloy. A substitutional alloy is when you have two atoms of similar size. And what happens because they're similar size is that one substitutes in for another. So here we have two atoms of similar size. Maybe we have palladium and silver right next to each other on the periodic table. Palladium and silver, we have one substituting in for another. When you're focusing on alloys, we almost always see particle diagram questions with alloys. Look at the sizes of the atoms in the question. If they are different sizes, right, so that means that you need to know atomic size. If they are different sizes, it's going to create an interstitial alloy. If they are similar in size, so they're both transition metals, they'll create a substitutional alloy. So those are our two different types of alloys, which are both metallic solids.
You said interstitial, the small ones are non-metals?
Yeah. Yeah, they're typically non-metals. So a lot of times we see carbon filling in the holes, maybe oxygen. So some oxides we'll see fill in the holes as well.
Wait, so the bigger ones are cations then?
Bigger ones are just metal atoms.
Not cations are smaller.
No, these are just, so these aren't charges. These are just like Fe or just like Cu. Yeah, so the metals themselves aren't cations. They're actually just neutral metal atoms. And then we have neutral nonmetals filling in. Yep. So 2.5. So now we switched from the types of bonds to actually creating structures. So topic 2.5 itself says you need to be able to draw Lewis structures. That's basically what it says. And so what I did is I just took a screenshot of our notes from Lewis structures and put them on this slide. Lewis structures were chapter 8 as well. You have these handwritten notes. This was from chapter 8. So remember with Lewis structures, you count your valence electrons. Always, always, always count your valence electrons. Remember, your valence electrons are based on the location of the periodic table. So lithium, that group has 1 valence. Beryllium's group has 2. Skip the transition metal, 3, 4, all the way up to 8. So count your valence electrons. Remember about ions. So if it has a charge, you're either adding or subtracting electrons. Make a reasonable formula. So remember, the least electronegative atom goes in the middle. Typically it's carbon. If we have carbon, carbon will go in the central. Hydrogen always wants to be on the outside. And then start by adding bonds. If you have cons, C-O-N-S, remember you could potentially multiple bond. If you have cons to help you determine what type of multiple bond, you can use the 6n+2 rule. So the 6n+2 rule, n is the number of atoms except hydrogen. And then you either have a difference of 2 electrons or 4 electrons. So from there, you can either figure out, well, I need 1 double bond, or I need 2 double or 1 triple. So that's looking at drawing your Lewis structures. Always make sure you're following the octet rule. So every atom needs 8 electrons except for hydrogen. But if your central atom is in row 3 or below on the periodic table, the central atom could have an expanded octet. So sulfur might have more than 8 around it if it's the central and you need somewhere for lone pairs to go.
For ions, whenever you draw it, don't you have to have like the brackets?
Yes. Yeah. Yeah, if it's an ion, whether it's a cation or an anion, when you draw the Lewis structure, you want brackets around it with the charge up in the corner. Now, when we draw Lewis structures, we could have resonance structures. So 2.6 talks about resonance structures and formal charge. So sometimes you can have 2 or more Lewis structures that can represent 1 molecule. We looked at some polyatomic ions, CO3 2-, have 3 resonance structures. In a resonance structure, the arrangement of the atoms do not change. So down here shows you 2 resonance structures of NO2. Notice the arrangement of the atoms don't change. It's still O's on the outside and in the middle. However, we have, again, this term delocalized. You have delocalized electrons. The electrons could potentially move between the atoms. So we could have a double bond on one side, or we could have a double bond on the other. Another way to represent it is with the dotted line. Because we have this resonance structure, this actually creates equal bond lengths. So notice, this is how we represent resonance structures. In reality, it's a blend of these 2. We don't have one bond that is longer than the other. These actually both have the same bond lengths. We would actually say this is a bond order of 1.5 because you have 1, 2, 3 bonds between 2 locations. So resonance structures, we see the same bond length because it's actually a blend of the 2. Now, sometimes we draw a structure and we're not sure which one might be the best. Now, both of these are resonance structures. We don't have any other way to draw this. We looked at an example of carbon dioxide. When we looked at formal charge, we looked at carbon dioxide. When we're looking for the best structure, that has all or most of the atoms with a formal charge of 0. If you have to have a formal charge, it puts the negative formal charge on the most electronegative atom. If we look at the example that we did during the year, we had this as an example. When you look at CO2, you could, if you do the 6n+2 rule, you find that you either need 2 double bonds or 1 triple bond. And so we can actually look at which of these structures is the best. Now remember I gave you a hint and I said the more symmetric, the better. But that can't be our reason as to why it's the better structure. Our reason has to be formal charge. So here I said, remember when you want to calculate formal charge, use the circles. Formal charge is calculated. Now, you actually have a formula you could use. I don't ever teach the formula. I just teach the circle method. The circle method, you draw a circle around every atom and you split the bonds in half. So I can do the same thing for the other one. Draw a circle around every atom, split the bonds in half. To calculate the formal charge, you do valence electrons minus the number of electrons in the circle. Right? Valence minus circle. Oxygen has 6 valence electrons. I know that because of its location on the periodic table. It's in group 6. It has 6 valence. If I look in this circle, I have 1, 2, 3, 4, 5, 6, 7 because I split that single bond in half. Well, what's 6 minus 7? -1. So this oxygen has a formal charge of -1. Carbon has 4 valence electrons. Again, look at its location on the periodic table. 1, 2, skip the transition, 3, 4. Count the electrons in the circle. 1, 2, 3, 4. This carbon has a formal charge of 0. 1, 2, 3, 4, 5. This oxygen is +1. So you have -1, 0, +1. You do the same thing for the other one. Every atom is 0. So the reason that CO2 with 2 double bonds is the better structure is because the formal charge on every atom is 0. So that's actually a reason for why one structure is better than another. It's formal charge. So for 2.7, this is VSEPR and hybridization. VSEPR is shapes. For us, shapes were chapter 9. Shapes were chapter 9. So I actually took this right out of our chapter 9 notes. Remember, there's a difference between electron domain geometry and molecular geometry. Electron domain is just based on the areas of electrons around the central atom. It's one of the fundamental shapes. One of these 5 fundamental shapes. In terms of bond angles, the only bond angles you need to know are these. 180, 120, 109.5. Trigonal bipyramidal, remember, has 2 bond angles because of axial and equatorial. And then octahedral is 90. Molecular geometry takes into account the bonds and the lone pairs. So you notice you start with trigonal planar, but then your lone pairs will push the bonds down, and that forms a bent shape. In terms of angles, for this, we would just say the bond angle is less than 120. So you look at what fundamental shape does it come from. The bond angle will be less than that. Remember, this is when we did all of the balloons. We popped the balloons to represent lone pairs. So then we have trigonal bipyramidal fundamental shape, octahedral fundamental shape. Again, that was all chapter 9. With this, you have to be able to look at geometry, bond angles, bond order. So bond order is based on what type of bond. Single is bond order of 1, double is bond order of 2, triple is bond order of 3. Bond lengths. Is the molecule polar? Remember, presence of lone pairs typically results in a polar molecule. And then finally, hybridization. You need to know 3 hybridizations. I taught you more than 3. We actually went into the d orbital, or into the d sublevel. You guys just need to know if there are 2 areas of electrons around the central atom, it's sp hybridized, right? 1s, 1p, 2 areas of electrons. 3 areas of electrons, 1s, 2p, so sp2. 4 areas of electrons around is sp3 hybridized. Those are the only hybridizations that you have to know. And then finally, sigma and pi bonds, single bonds or sigma bonds. The first bond of a multiple bond is sigma, the rest are pi. So a double bond is 1 sigma, 1 pi. A triple bond is 1 sigma, 2 pi.